My name is Noah Civiletti.
My name is Cyril Cook.
My name is Maria Kinsey,
And I'm Elaine Liu.
and in this past summer, we were granted the opportunity through UNCW, to which we conducted an undergraduate study by using machine learning models to predict the presence of hereditary cataracts and pathogenicity from alpha B crystalline mutations. We would also like to give thanks to our amazing instructors and our contributors, such as the Summer Ventures UNCW Biotechnology class. Now, what is the problem at hand? Currently, 20,000 to 40,000 children are born each year with hereditary cataracts. Now, this disease is also rather understudied, and it is also unknown as to which specific gene mutations cause this. Therefore, the sooner cataracts are detected in children, the sooner correctional surgeries and treatment can be better given to reduce the risk of long-term vision problems. This process of checking babies for cataracts is also pretty difficult and tedious at the moment, to which it requires routine examinations within 72 hours and 6 to 8 weeks of birth. Now, biologically speaking, we're going to be focusing on the islands, which are transparent biological tissues that focus light to the back of the eye. Cataracts are typically formed due to old age or because of damage to proteins in the island's center. Now, what makes hereditary cataracts such a rare condition is that it causes blindness in younger individuals due to gene mutations rather than natural aging. Furthermore, the main alpha crystalline protein is most common and composed of two slimmer types of protein chains that form large complexes containing about 40. These protect against heat-induced protein aggregation, and they also enable proper refolding of denatured enzymes.
So this brings up our research question. Can a machine learning model be created to predict whether certain alpha B crystalline mutations lead to hereditary cataracts? Now, this is an example of the data we received. We received 40 alpha crystalline mutations where 14 of the mutations were positive, meaning that they had hereditary cataracts, and 26 of the data points were negative, meaning they had the alpha B crystalline mutation, but there was no hereditary cataracts present in the subject. Now, here are some other important terms we're going to be talking about for the rest of the presentation. There's isoelectric point, which is the pH value of the amino acid when it carries no net electrical charge. There's solvent area, which is the amount of solvent the amino acid has access to. There's delta delta G, which is the change in Gibbs free energy. If delta delta G is negative, then the mutation destabilizes the amino acid. And if it is positive, the mutation actually stabilizes the amino acid. And lastly, there's evolutionary age, which is the abstract amount of time the amino acid mutated from its original state. And PDEL is just a standardized version of evolutionary age. Now, before looking into models to classify the mutations into the positive and negative group, we decided to do an exploratory data analysis where we just compared a bunch of different variables together to see if we can find any relationships. And on the screen right now is some relationships we thought were important. So we found that evolutionary age as PDEL and isoelectric point and solvent area and isoelectric point showed a relationship. So you can see the red points are the negative group. So the group that did not have hereditary cataracts, they all have like they all have an isoelectric point of about 6.7 to 6.8, and all of the positive mutations are away from this value.
Now, in order to figure out which machine learning model would best fit our data, we decided to use a train test split cross-validation, which randomly put the data into two groups. 75% of it went into training to train the models, and the other 25% went into testing. Now, we tested 9 different machine learning models, which were logistic regression, LDA, KNN, SVC, decision tree, bagging, random forest, ADA boosting, and gradient boosting. And after testing all these, we found that KNN, SVC, and adaptive boosting had the highest average accuracy, specificity, precision, and F1 score. Now, through the Summer Ventures program, we had the opportunity to collaborate with 4 biotechnology teams, which each produced their own unique data set. And here you can see that we tried out our machine learning models on all of their data sets. And because of their varying data, we had varying accuracies with the different models. But as you can see, KNN and SVC remained on top throughout all of the models.
So as Sam said, SVC models, or support vector classification models, worked extremely well. So SVC models work by creating hyperplanes that are farthest away from data points on either side of them, thus separating the data points into different classes. So SVC models with our data, and especially covariates of isoelectric point and solvent area, performed really well with average accuracies of around 95%, and also really high specificities and precisions and F1 scores, as well as really low run times. So ultimately, SVC was chosen as the best performing model holistically and overall for a couple of key reasons. First is that other models like adaptive boosting or AdaBoosting had much higher runtimes, and also models like KNN, by virtue of how they work, are a lot less sturdy and consistent when more data comes in, due to them being more susceptible to changes from outlier data observations. This is really key, especially because we work with the biotechnology students who continuously bring us more data to test and train with. So with our SVC model, we had a final accuracy of 95.3%, which was really positive as a result, and then also a sensitivity or a true positive rate of 90%, as well as a specificity or true negative rate of 98.4%. So overall, really promising results.
So using the SVC classifier with isoelectric point and PDEL as covariates, we created a prediction tool that would be able to predict the likelihood of a mutation being pathogenic given its biochemical characteristics. And here you can see the output of that tool, which includes its prediction, its confidence in both positive and negative, and here you can see the true value too, to see the accuracy of our predictions. Now, we wanted to create a tool that could be used by other researchers within the field who are in biotechnology but not in machine learning. So we created a .exe file that would be simple to use for people even without machine learning experience. So you'd put in an Excel file with the initial data and be outputted another Excel file such as this one, which has the predictions and the confidence values.
So we have overall two key findings from our research. First, that SVC, KNN, and AdaBoosting models show really good potential for being used to predict pathogenicity of alpha-B crystalline mutations, with SVC being the most efficient overall. We also saw that isoelectric point and evolutionary age as PDEL values are variables that when they are covariates, show really high promise for providing more biological and biochemical explanations for why certain mutations over others actually lead to hereditary cataracts. We also have two key contributions from our research. First is a novel method of predicting pathogenicity and presence of hereditary cataracts from alpha-B crystalline mutations with really high accuracy. And second is our predictor function that allows easier access to detect mutations that would lead to hereditary cataracts for not only other researchers, but also eventually professionals working in the medical field. And there are three key steps we want to take moving forward with our research. First is to work further with biotechnology students to gather more data to train and test with to further improve the model we have. Second is to further test the hyperparameters or covariates and to implement other cross-validation measures to ensure that the model we actually have is the best it can be. And third is to further develop and test and use the function we have in medical spaces for children so that tens and thousands of children can sooner receive treatment measures that they need. Here are references. And thank you. Please send us any questions you have.